Okay, welcome back. Today we want to look at 7.2. Um, okay, so this is about functions still. So in particular, one-to-one and then inverse functions and onto functions as well. Okay, so 7.2, we have one-to-one, onto, and then inverse functions. And the literature, if you, into inverse, what did I just write? Inverse. In the literature, you're going to see all kinds of different names for it. If you take like advanced calculus or something, like surjective, injective, bijective, those things are all sort of interchangeable with these definitions. Um, anyways, injective, that first thing there, the oneness, one to one, is injective. Basically, that means you're not going to have any case where two different elements are going to the same element. So it's a function, so it passes the vertical line test, but it's also one-to-one, which means it'll pass kind of a horizontal line test as well. So it's a very restricted class of functions. Let's get a working definition that we could use in proofs. So we let f be a function, big F, going from the set x to the set y. Okay. So we'll say that this thing is one-to-one. If and only if for all x1 comma x2 in the set x, let me write it here, if big F of x1 is equal to big F of x2, then x1 must be x2. Okay. We can negate this and have kind of a working definition for proving something isn't one-to-one, okay, which usually you just have to find a counterexample to prove this. So it's not one-to-one if and only if, and we just go through and negate this universal statement. So there exists an x1, x2 in the set x, and you change the implication into an and with a not on it. So such that then such that f of x1 equals f of x2, and then x1 is not equal to x2. Okay, so before we get into kind of the proofiness stuff, let's take a second to think about these as pictures. Okay. So an example of something that's not one-to-one would be something like the following. So maybe this guy goes here and this guy also goes here. So that's bad news in the world of one-to-oneness. So like I said, it has to be a well behaved function. Maybe put another guy there. So it has to go like this to this, this to this, and this to this. So for every one thing over here, there's only one thing over here. And if this guy here equaled something else, then the x term that went to it had to be the same. Okay, so you can have things that aren't kind of covered by the range in the codomain there. We'll talk that'll be related to onto, being onto. Okay, so up there, one-to-one, onto, inverse. Onto is the idea that everything in the domain is in the range. Okay, okay. So anyways, let's take a look at playing around with these. The proofs type, the proofs for being one-to-one aren't that hard. So number 11, part A, we have this function going from the integers to the integers, and we define it by g of n equals 4n minus 5, okay, for all integers n. So is g 1 to 1, right? So they'll be asking questions here. And yeah, it is. So we have to prove it, right? It's just the graph of a line if you were to graph it out. So, but in this case, in the integers, so it's a bunch of dots. So it's not continuous, you know. But it's essentially the equation of a line. So it's going to be 1 to 1. Okay. So anyways, we have to prove that. So what do we do? We're going to suppose. So going back here to our working definition. On the right part of it, we want to suppose that we have kind of picked some arbitrarily chosen values in the domain. In this case, the domain is the integers, and on top of that, we suppose that, you know, f of x1 is equal to f of x2, or in our case, g of n1 is equal to g of n2, right? Okay, so we're supposing n1 comma n2. Let me change color. Are payback integers in this domain Z. Okay. Also supposing then g of n1 equals g of n2. Okay, so what we'll do is work with the definition of g and then use algebra to show n1 is equal to n2, which is the ending point on our working definition for one-to-oneness that I'm circling here, or boxing in yellow. Okay. Okay. So we note then we're starting with g of n1 equals g of n2. By definition, then we could rewrite this as, I got to scroll up to the definition there. So by subbing in n1 on the left-hand side, 4n1 minus 5. On the right-hand side, 4n2 minus 5. Okay, and from here we just use algebra. Okay, so you can add 5 to both sides. You get 4n1 equals 4n2. Then you can divide both sides by 4, and you get n1 equals n2, which is what we're trying to show. And this proves that G is 1 to 1. Okay. Okay. Algebraically, some of these get a little bit harder. If you have a more complicated formula, you're probably going to have to kind of engineer some other approach. For the ones we deal with, they're usually pretty simple, and they won't give you headaches. Okay. Okay. Let's look at one where we're just saying that something's not 1 to 1, and this just comes down to finding a counterexample where if you look back up at our definition on and look at the left part of it for the second, so this is like 1 and this is 2 here. We just need to find a place where f of x1 equals f of x2, and then x1 does not equal x2. Okay, so we need to find these two numbers that kind of screw it up. Okay. Okay. So this is number 13. They give us this. Let me change color. They give us this function h from the real numbers to the real numbers, defined by big H of x equals x squared. Okay, so it's a parabola. We know it's not going to be 1 to 1. It fails the horizontal line test. In particular, there's an x1 here and x2 there, such that f of x1 equals f of x2, but x1 does not equal x2. Okay, so we just need to show that or write it out, not with a picture, but in words, so another human could understand. So they're asking, is h 1 to 1, And of course we say no. So let basically x1 equal -2, and then x2 equal -1. In this case, h of x1, which is -2, equals 4, which equals h of whoops, this one I want this to be, sorry, 2. I have no idea what my brain was doing there. Sorry. Okay, so yeah, h of -2 is -2 squared, which is 4, and then h of +2 is 2 squared, which is also 4. Okay, so here we have h of x1 equaling h of x2, but x1 does not equal x2, okay, which basically fulfills the definition for not being 1-to-1. Okay, so hence it's not 1-to-1. Okie dokie. So that version is a lot easier. There's some stuff on hashing functions in the book. You may be interested in that if you're more of a computer science person. I'm just going to skip it because I don't think it's in the homework. And some people aren't really computer science majors in this class, so I'm just going to let it go. You can read it if you want. Okay. Okay. The second topic then is onto functions. And another phrase you may hear in the literature is surjective. Okay. Surjective functions. So 1-to-1 injective, onto surjective. If it's both, it's called bijective. Okay. Okay. So anyways, given big F function such that big F goes from set x to some set y, we'll have some working definitions for onto. Okay. And it just means that everything in the codomain is in the range, basically. So there's an element going to every element in the codomain. Okay. So F going from x to y is onto if and only if for all y in y there exists some x such that big F of x is equal to that y. Okay. And then we can negate this to get a definition for not onto. Okay. And that's if and only if there exists a y in y such that for all x I guess I should say in the domain, right? So for all x in the domain, f of x is not equal to that y. Okay, so you just negate the predicate there. Right, so proving onto is a little more complicated than not onto. For not onto, all you have to do is find that counterexample again. But anyways, let's try working with this. So proving onto. A little more complicated than the proving one-to-oneness, right? So proving one-to-oneness, you kind of just use the definition and then algebra and then you're done. Proving onto, you kind of have to back engineer this particular element y in the codomain, or sorry, you have to back engineer the particular x in the domain such that f of that x is equal to y. Okay, so how does that work? We're going to suppose y is any element in big Y, and then we'll back engineer or construct an x in x such that big F of x is equal to y. Okay, so it's hard because that construction isn't necessarily going to be in the proof. You kind of have to do it to the side and then write up your answer. So when you read these proofs, it looks like, oh, how do you magically figure out that this thing equaled x, or sorry, this thing, once you put it into the function, equals y? Yeah, that's the weird part. Okay, where did that come from? It's scrap work. Fortunately for us in the homework and the software, they kind of include the scrap work. They'll do like a little box, and they have you kind of engineer the expression. Okay, but anyways, let's take a look at number 11, part A. We'll do a counterexample type first, so we're going to show that this thing is not onto. So we have g from the integers to the integers using the rule g of n equals 4n minus 5. Okay, so if it was onto, for every integer there should be a corresponding another corresponding integer such that g of that integer is equal to that other integer. And okay, so let me write this out. So onto is going to be no. Okay, so notice 1 is an element in the integers, okay, which in this case equals our codomain, right, which we've been calling y. Then also note finding that value of n, that would give us 1 in that codomain, right? So note we sort of have to solve for it. So instead of letting g of n equal, all right, so we go g of n equals 4n minus 5. We want it to set g of n equal to 1, right? So we're hoping to find this magical n value in the integers that gives us 1 when we put in n into g of n. Okay, if you try to solve for n, you could, you see it. 4n, if I add 5 to both sides, is 6. And then dividing by 4 is the only solution to that equation is 3/2, which isn't an integer. Okay. So we notice the only solution here is not an integer. So this is a number in the domain, which is not going to have a corresponding number. Sorry, this is a number in the codomain that's not going to have a corresponding number in the domain, right? So basically, then you're saying that there exists a y such that for all x, f of x does not equal 1. So hence, the number 1 is a number where g of n does not equal 1 for all n in the integers. Okay, so it's not onto. It doesn't, basically, I guess you could think of it as covering. I don't want to say that because that's kind of a restricted term when you talk later about compact sets. Okay, but let's move on to the other version, which I think is a lot harder. Usually you can kind of guess, these counterexample types, but the constructing proofs a lot more work, right? So anyways, you have this function going from the set of reals to the set of reals, defined by this formula g of x equals 4x minus 5. We want to show that this thing is onto. Okay, so show g is onto. Okay, so going back to our working definition, what do we have to do here? We want to take an arbitrarily chosen y and y, and then kind of find this x and x such that f of x equals y. So we kind of start with this junk in the box here, and then we'll kind of illustrate that this works. Okay, that f of x then is equal to y. Okay. Suppose then y is a particular but arbitrarily chosen element in the codomain here, R. So this is where we have to do the back engineering. Okay, so and they'll probably do like a little box or something. And so how do you do it? You're kind of going to do just what you did back here when you were proving it didn't work. You kind of produce a formula from that. Okay, so note letting y, and it's basically just finding an inverse, right? Y equals 4x minus 5, and then solve for x. Okay, so 4x equals y plus 5, and then x equals y plus 5 over 4. Okay, so that's what we're going to do. We're going to let x equal y plus 5 over 4. Okay, we then note it is in the domain. You have to have that part to be true. We note x is the ratio of y plus 5, which is the sum of real numbers and therefore a real number. And 4, which is non-zero, which is a non-zero real number. Ratios of real numbers are real numbers. Also, you have to kind of assuming also that the real number in the denominator is not 0. Hence, x is in the domain. This x that we've constructed is in the domain. Okay, so we need that to hold for us to now consider f of x. Next, consider f, or is this function called f? No, it's called g. Consider g of x, and note. And now we just do substitutions and definitions. So g of x is equal to g of this, y plus 5 over 4, which is equal to, then we use the definition, 4 times y plus 5 over 4 minus 5. And then we could use arithmetic to simplify. And we've shown that we found an x in the domain such that g of x goes to this randomly selected y value that we started with, and hence that shows it's on to, and hence g is on to. Okay. Finally, then, if you could show that something is one-to-one and onto, it's invertible. Okay, so inverse functions. So suppose big F goes from x to y is a one-to-one onto function. Which they sometimes also call one-to-one correspondence. And they also call it a bijection. It's hard enough remembering one definition. It's even worse when they have 3 different terms for that one definition. Okay. Anyways, suppose that this thing is a one-to-one onto function. Then there will exist this function f inverse of y, which equals x, such that f inverse of y equals x if and only if y equals big F of x. Okay. So we could talk about this inverse function then. So yet another definition. Basically, f inverse of y is the unique element x in the set x such that big F of x equals y. Okay. Okay. Then you'll probably have problems where they want you to first prove it's one-to-one, then prove it's onto, and then find the inverse function. Okay, so 47 is like that. I don't think there's one in the homework that's totally like that, but they'll probably have you find the inverse, and that's pretty simple. Just note, for g inverse of y, we note g of x must equal y. That's just sort of from the definition. And this is true if and only if y equals y plus 5 over 4, or sorry, x equals y plus 5 over 4. So sort of back engineering that expression. And that will give you the inverse. Okay, so this thing is basically g inverse of y. Okay. This is basically just what you do when you're back in pre-calculus. Okay, they make it a little more formal in the book, but it really is just a matter of solve this equation for y at the end of the day. You can chain it together with definitions and stuff, but I mean, okay, let's leave it at that. And okay, thanks for watching. See you next time.